Hi ladies and gentlemen, in this video we discuss the conversion of flip-flops. How do you convert one flip-flop into another flip-flop? Already we have seen the conversion of SR flip-flop into D flip-flop and SR flip-flop into JK flip-flop. Now we see more conversions like a D flip-flop to a JK flip-flop, then a D flip-flop to a T flip-flop, etc. So let me start with that presentation. The speech is organized into your learning outcomes, conversion of a D flip-flop to a JK flip-flop, and a D flip-flop to JK flip-flop in Verilog, and then a D flip-flop to T flip-flop and a T flip-flop to D flip-flop, and the simulations in QX. These are simple simulations which you can do in Verilog as well. You can do on your own. And the summary of understanding. So what you will learn in this video is you will learn to convert a D flip-flop to a JK flip-flop. Then you will learn to implement a JK flip-flop with a Verilog, that is an edge triggered flip-flop. Then you will learn to convert a D flip-flop to a T flip-flop and back. So first let us consider the conversion of a D flip-flop to a JK flip-flop. So you can convert a one flip-flop to another by adding additional suitable combinational logic. So you have learned in the conversion of SR flip-flop to JK flip-flop, you have seen by adding two AND gates at the input and providing additional feedback. Then you converted an SR flip-flop to D flip-flop by converting an inverter between S and R. And then you saw the conversion of a JK flip-flop to a T flip-flop by adding an inverter between J and K. Then you made a JK flip-flop into a T flip-flop. In the last video you have seen by connecting a J flip-flop with J and K shorted together to form a T flip-flop. Now we see the remaining conversions also. Now it is very easy to convert a D flip-flop to a JK flip-flop, because for a JK flip-flop we know that the model is Qn plus 1 is Jn Qn bar or Kn bar Qn. So it can be directly implemented, because if this is given, it is the Qn plus 1. If this if this function is given to the D input of the flip-flop, Qn plus 1 will be Dn. That is a property of a D flip-flop. Qn plus 1 is Dn, that's the previous input. So if I give this input to the D input, then the D flip-flop becomes a JK flip-flop. So you can see that this is a circuit diagram. This is a D flip-flop, this is an edge triggered D flip-flop, let that be an edge triggered D flip-flop. Then I connect it here. This is this Q bar is connected to this AND gate, so that this output is JQ bar, JQN bar, and here K is inverted, and here this AND gate is connected, this input AND input is connected to Q, so that this is KQ bar, Q bar K, Q K bar, I'm sorry, K bar Q. So this output of this OR gate is JQN bar or K bar QN. So this becomes a DN, which in turn becomes QN plus 1. So the whole circuit, this acts as a D flip-flop. Now I will show you the simulation of this in QX. We will see. We have already seen this simulation in the last class, but we saw the QX model only. Now we see the Verilog model of a JK flip-flop. We saw this simulation earlier when we discussed the T flip-flop with J and K shorter to 1. In the last video we have seen that, but we haven't seen the Verilog model. So we can make a Verilog model for D to JK flip-flop conversion this way. What if you look here, you can see that outputs and inputs are Q bar are the outputs, and JK clock clear and preset are the inputs. So these inputs are declared here, and some internal wires or local nets are also declared. Here, if you look into the end of this one, here you can see that these four lines declare the four lines, they realize my combinational circuit So this is j q bar. This AND gates give me j q bar. This O7 is j q bar, and this is k bar is k complement. This is a NOT gate. Then this AND gate, this gives me q and k bar. So when I add this when I over this O7 and O8, I get the D input to the D flip flop, input to the D flip flop. This which is j qn bar or k bar qn. So this D is given to the input of a D flip flop. These lines create a D flip flop with a clear and preset. Okay. So this way you can realize its output is Q and Q bar. So this realizes the JK flip flop with a D flip flop. Now we can run the simulations here. Now I can make a test bench also. This is my device, JK FF Edge. This is my device. Okay, and I can write a test bench for this. That is, here I have a test bench for this. You can see that this device is included here, and this test bench is written as usual. Now we can run this. I can run this code here. I can write I Verilog .v. Now that is compiled without any error. Now I have to run the test bench. Minus o a dot out. Okay, now you can run this a dot out dot slash a dot out, and you can see the operation of the JK flip flop. Okay, here initially this preset is 0, so q is 1 and q bar equal to 0. Then here clear equal to 0. These are asynchronous input. When clear equal to 0, q equal to 0, q bar equal to 1. So these are response to asynchronous inputs. Now here in these lines, clear and preset are held high so that synchronous inputs do play the role. So here clock equal to 0, so it stays in the previous state. Here j equal to 1 and k equal clock equal to 1, so it toggles. Q equal to 0, it becomes q equal to 1, and q bar equal to 1 becomes q bar equal to 0. That is the last condition of the flip flop. Here it is 0 1 with the clock equal to 0. Nothing happens to the output because the clock is inactive. It stays in the previous value. Here it is 0 1 with the clock 1, so output q becomes 0 and q bar becomes 1. Again here clock equal to 0, so no change happens. Here j equal to 1 and k equal to 0 with clock active high, so now the state changes to q equal to 1 and q bar equal to 0. Here 0 0, here it is 0 0 with the clock 0, no change happens at the input. Here at 0 0 with the clock 1, that is the previous state, it remembers the previous state. And at here j equal to 1, k equal to 1, clock equal to 1, again toggling happens. It toggles to 0 and 1. So this is how the operation of JK flip flop is observed. Now let me go back to my presentation. Now this, let us look at the conversion of a D flip flop to a T flip flop and back. Now this is how the conversion is done. I have to convert a D flip flop to a T flip flop. So between this T input and the D flip flop, there is some kind of combination circuit. So this output D should be a function of course, all these things are functions of Q. So this combinational output, circuit output, that is a input to D, that should be a function of T and Q. Tn and Qn. So the combinational circuit should be designed. So how do I do that? I have to look into a truth table for this one. So that truth table appears here. So here I have this this Qn plus 1 is a function of Tn and Qn. If you look into this thing, this Qn plus 1, which is actually Dn, this is a function of Tn Qn. So I write it in terms of Tn and Qn for 0, 0, 0, 1, 1, 0, 1, 1. So what is Qn plus 1 here with Tn equal to 0, Qn equal to Qn stays in the same state, so Qn plus 1 is 0. Here Tn equal to 0, so Qn plus 1 remains at 1. And with Tn equal to 1, Qn equal to 0, Qn plus 1 becomes a 1 because this is a toggling condition. And with Tn equal to 1 and Qn equal to 1, this Qn plus 1 becomes a 0 because toggling happens. Now there is a change from Qn to Qn plus 1. So if what should be the value of d here? Because this is a 0 0, because then d should be 0. Qn does not change, it remains at 0. So dn should be 0, because you know the property of dn, that is dn is Qn plus 1. So dn should be the same thing as Qn plus 1. So it is 0 1 1 0. So from this truth table you can know that dn as a function of tn and qn, if I write, it is tn XOR qn, because this is a truth table of an XOR function. This is tn XOR qn. dn is tn XOR qn. So this is how I designed that. dn is tn XOR qn. So that circuit diagram looks like this. This is my D flip-flop. This is a T input. This is Q. This is D is T XOR qn. So this is how I achieve the conversion of a D flip-flop to a T flip-flop. Okay, I will say this truth table once again. Qn plus 1 is a function of Tn and Qn. So this Tn Qn can be a 0 0 0 1 1 0 1 1. So Qn plus 1, if the since Tn equal to 0, here there is no change, it remains at 0 1 1. Here Tn is 1, so there is a toggling. 0 changes to 1 and 1 changes to 0. Now what should be the value of dn to affect such a change? You know that dn is Qn plus 1, so dn is 0 1 1 0. Now the question is, what is dn in terms of tn and qn? So here, by looking at this table, this truth table, you can say that dn is tn XOR qn, and that is this equation 2. Now if I realize this equation, so this combinatorial circuit is in effect, it's an XOR gate. So it is here d is t XOR qn. So this D flip-flop becomes a T flip-flop. Likewise, I can make a T flip-flop to a D flip-flop like this. If I look into this truth table, so this is T should be a function of dn and qn. So if I say dn and qn 0 0 0 1 1 0 1 1, what should be value of qn plus 1? Because qn plus 1 is dn, because for a D flip-flop qn plus 1 is dn. So this qn plus 1 column becomes 0 0 1 1. And so now there is a change of qn to qn plus 1. What should be the value of tn to affect such a change? Here it is no change, 0 0, so tn should be 0. It's a toggling here, 1 to 0, so tn should be 1. Here also toggling from 0 to 1, this tn should be a 1. And from 1 to 1, this tn equal to a 0. So here also you can see that tn is 0 1 1 0, which says that tn is dn XOR qn. Tn is dn XOR qn. So that is equation 3. So if I realize this equation 3 as a circuit, that will look like this circuit. This is my T flip-flop. Now I have to convert it to a D flip-flop. So here also I have the XOR circuit. So this T input is D XOR qn, dn XOR qn. So this setup works like a T flip-flop, and this works like a D flip-flop. Now you can observe the simulation in QX this way. Here first I will see a D to T conversion. Here it is this. Here it's a D to T conversion. So this flip-flop acts like a T flip-flop. Now this T is kept at 1. Now this is a D flip-flop with a clear and preset kept at 1, and this a negative edge triggered, I think. So if I run this simulation, you can see that toggling happens this way. This here T is kept high, and this a negative edge triggered flip-flop. So change happens at a very trailing edge. So here T is kept high. Initially Q is 0. Now here it toggles. It stays this way. Here it toggles again. At the next clock cycle it toggles again. Okay, this acts like a T flip-flop. Or you can add a signal and observe this. t equal to 0 condition also you can observe. Here you can see that initially this t equal to 0, so here no change happens at this 2 nanosecond, no change happens, it stays here. And here it's a 1, t becomes a 1, and at 4 nanosecond at the first next trailing edge it changes state, and it comes here again. Here t is a 1, so it again changes state. Here t equal to 0, so no change happens. T equal to 0 means it stays in Qn plus 1. Again here t equal to 1, so at the next trailing edge it switches to 1, from 0 to 1, that way. So this is how I realize a D flip-flop, a T flip-flop with a D flip-flop. So what you need is a D flip-flop and an XOR circuit, and these are connected this way. It works like a T flip-flop. Now let us see the simulation of a T flip-flop with a T flip-flop as a D flip-flop. How we configure a T flip-flop as a D flip-flop. Now you can see here this is a T flip-flop with set and reset, the preset and clear values kept at high, and this Q is connected to the input of an XOR gate. The other input is given to your D input. Now you can run this simulation and observe that it's a D flip-flop. Now you can see that this is a waveform. Here you can see that Qn plus 1 is equal to D. Here this is an active. Here you can see that at the negative edge this remains in here the flip-flop is active. Qn plus 1 is Dn, so Dn is 0 here, so it remains at 0. And at this end you can see that D input is 1, so the output changes to D. Qn plus 1 becomes D. And here again here you can see that at the next clock edge D equal to 0, so it becomes 0. Qn plus 1 becomes 0, and it stays here. Here at this 8 nanosecond there's a trailing edge, again it goes high because the D input is high. So this is a working of a D flip-flop. So this is how I configure a T flip-flop as a D flip-flop. Now that you have understood this simulation, let me go back to my presentation. Now coming to the end, what you have learned in this video is you learned to derive a D flip-flop from a JK flip-flop from D flip-flop. So how did I do that? Because I know that the model is JQn bar or Kn bar Qn. I realize with a combination circuit and give that as a input to D. So you know that Qn plus 1 is Dn, so Qn plus 1 becomes JQn bar or Kn bar Qn, which makes the D flip-flop, which makes the JK flip-flop. So then you learn to implement a JK flip-flop with Verilog, the same thing, a D flip-flop that is configured as a JK flip-flop that we realized in Verilog, and we understood the simulation. We saw that is working as a JK flip-flop. Then you learn to convert a D flip-flop to T flip-flop and back and vice versa. So you saw the simulation in Qx and verified the operation. And that is the end of this presentation. I thank you all.